In this part, we will go over the basics of vehicle control. First of all, the vehicle that we're going to be using in this course is called a Turtlebot 3, and the model is Burger because it's shaped like a burger. It has these layers. It sort of looks like that. And it's a mobile robot that it's used a lot in research. And it's based on this robot operating system that we'll be using. And the name Turtle comes from that because the logo of robot operating system is turtle, so that's why it's called a Turtlebot. So in here on the top we have a LiDAR for simultaneous localization and mapping and navigation. And so this thing spins around. There's a laser pointing to whatever is there or is not. And as this thing spins, it sort of looks like an ice hockey puck. And as it goes, sorry, it's this end here that does the sensing, and it spins around all the time, taking a lot of measurements. So you get from each degree of 360 degrees, you get a measurement of distance. And then there is this scalable structure because of these layers, which are sort of like Lego blocks. And the computer that's used in this Turtlebot is a single board computer called Raspberry Pi that's very commonly used in research and hobbyist projects for robotics. And it takes care of the algorithms, and it also has a internal measurement unit board attached to it, which does the odometry of the bot. Then there is an OpenCR board that is an open source motor controller that controls the motors. So the Raspberry Pi controls the OpenCR, and then OpenCR controls the wheels. Then the motors are there, two motors, and then there's one ball so that it has freedom to spin in place. So the one sort of metallic ball just keeps it in place. It's sort of the third point of contact with the ground. And yeah, there's a battery. Nothing too special about that. So before we go forward in the control basics, first of all, I want to go over the notation that we're going to be using in this course. So there are two wheels that are denoted. The speed of each wheel is denoted with W1 and W2, and I might use WI to just denote a wheel. So in the place of I, you might place 1 or 2. Then you have vehicle angular speed, so how fast it's spinning in place, that's radians per second. It's this heading that if we imagine that the sort of the default heading is this strike line over here, then the deviation from that is the angle. So how fast this angle is changing determines the vehicle angular speed. Then there is the vehicle linear speed, which is calculated from the speeds at wheel 1 and wheel 2. It depends, of course, about both of them to calculate the vehicle linear speed of the entire machine. Oh, I just noticed that this can also expressed as changes in x and y coordinates. So there's just beneath my picture, there's x dot and y dot. So in a way, you could also express this vehicle linear speed with two different variables, the changes in the coordinates. How much does the x coordinate change and the y coordinate? Then in this course, we will use both kinematic and dynamic models. Let's go over first what is a kinematic model. Kinematic models are based on motion, so you have a position and velocity and acceleration, and they're very simple because there's no forces acting on the model. It's sort of assumed that if the it's not only sort of assumed, but it is assumed that if the both of the wheels spin so that the speed at wheel 1 and the speed at wheel 2 is at both its 5 meters per second, then the speed of the vehicle is 5 meters per second. There's no resistive forces or slip or anything like that taken into account in kinematic models. It's assumed that there's no losses. So it's a very straightforward thing to do things, and it's quite trustworthy in low speeds and in good terrain. But then we have these dynamic models, which are based on forces acting on the vehicle, both internal and external. An internal force you could think of, gravity or the motors pushing the turning the wheels and then pushing the turtle boat forward. They tend to become more complex, even though you've all seen these F equals ma type models, which from you can then determine the acceleration and then the speed. So you get the same variables as these kinematic models. All right, moving on. So to basic control. So now we have this turtle over here. I portrayed it from the right side, and here we have, you could think of it as either of the wheels, 1 or 2. So we can spin them with the OpenCR board that we have, or moreover, you have a Raspberry Pi that controls the OpenCR board, so the power electronics controller, and then that controls the motors. So we know how to spin the wheels, but that's not enough, is it? Because even if we're just spinning the wheels, we actually want what we actually want to control is the linear speed of the vehicle and its heading, so how it turns and acceleration and deceleration of it, which is difficult to do intuitively just by controlling the speeds of two wheels, right? So yeah, so there's what I already said. The vehicle speed, the linear speed, angular speed are the ones that we actually want to control or give commands to these. So we need to make up some formulas that will transform the command of acceleration and braking and steering to respective vehicle speeds. Wheel speeds. So we have some parameters. We have the radius of the wheel, then we have the wheel speed, how fast it spins, and then the speed of the vehicle at this wheel. And if we now look at the turtlebot from above, from a top view, we have the two wheels here. In this scenario, the wheel 1 is spinning slower, and then wheel 2 is spinning faster, which then will make the turtlebot turn to right. So we have this center of rotation over here that is determined, like the center of rotation means that if we keep on going with these wheel speeds, the turtlebot will spin around this center of rotation. And so then the linear speed is the average of these two wheels, or more to put it forward, because we don't know the speed at the wheel, we actually just know how fast the wheel is spinning. So here's the formula. We need to take into the radius of the wheel. So this is how we're going to get the linear speed determined just from the wheel speeds. Okay, so now that we have the linear speed of the vehicle, next we need to determine what is the angular rate of rotation. So we have the same top view as we had on the previous picture. Here, the long large L is these yellow triangles, and the yellow triangle is beneath the red triangle. It's this long side over here, and then another side of this triangle is vehicle speed 2 from this end to here. And we can think of the relations of these two can be then extrapolated or used for because of the law of similar triangles to this red triangle where we have the length L is the wheelbase of the turtlebot, and then that's the longer side, and then the shorter side here is this vehicle wheels the vehicle speed at wheel 2 minus the vehicle speed at wheel 1. So this is the next step from, because this is true, so this also must be true. And now that we have a formula that has the angular rate of rotation and both of the wheel speeds included, now we can start to open this one up. So the next step is to do the same thing as in the previous slide, is to show or denote, for example, vehicle speed at wheel 2 with its radius and its wheel speed. And now that we have these minus signs over here, we can just change the order of the two and get rid of the minus sign on the front by doing that, and then taking the radius outside of the brackets. This is a bit tricky. It has a lot of notation here, and you might need to look it over a couple of times. But just start off by thinking the yellow triangle is the same proportions as the red triangle, and that's how we get this formula, and then we just move step by step by making it as simple as possible. Okay, then the next slide might be also quite daunting, but let's take it step by step, shall we? So we were looking at the vehicle speed, the linear speed. The formula for that is this part. So it was the radius of the wheel and then the average of the two wheel speeds. And that's how we get the linear speed, right? And by adding this cosine theta and sin theta components, we then have the we can split the vehicle linear speed into the component of the speed that goes into x direction, so x dot, and then y direction, y coordinate change, or y dot. So these two just might as well be v equals just this, but it's now decomposed to these x and y direction components. And then we had the heading that we just derived in the last slide. So this is called a continuous time model, but as we're doing computations and updating a model, you need to have some sort of you need to compute the model state at a certain point in time. We can't in real life everything happens continuously. There is no step time, so to speak. Things don't update every 1 second. They update all the time. But when we're doing numerical modeling, we need to have some sort of discretization of time, like what is the interval between a calculation. Like if we now calculate the turtlebot in this exact moment, when's the next time that we're gonna update the state of it? Is it after 1 second or a millisecond or something like that? That is a discussion on the next slide. What's the appropriate time interval to determine the time steps in a discretized time model or discrete time model. So, to calculate the next step, what is the x coordinate? So here in continuous time model, we're talking about x dot, so the change. But in a discrete time model, we're also always calculating what is the after taking one time step, what is the x coordinate then, what is the y coordinate then, and what is the heading then. All right, so first of all, you need to take into account the previous x, y, and theta parameters, what they were in the previous state, to calculate the upcoming state. Then we use this formula over here, and we give it the sort of magnitude in a way of delta t. So what is the time interval? So we calculate this thing, but if it's only the time has passed a millisecond, then the sort of weight or the difference, this term becomes much smaller, whereas the time interval is larger, it gives more weight to this one, hence then adding a bigger value to this x. These might be a bit tricky to understand. I will do a separate video where I derive these formulas, so it might be more understandable in that sense. But these are the ones that we will be using in the exercises. Okay, then shortly about the difference between continuous and discrete models, and how do you determine what is appropriate time interval. So let's think that this is some sort of a process. It can be the whatever it is. This continuous cyan, or let's call it cyan, this color, green, blue line is the actual behavior of this system. And then if we have a discrete model of the sample time is 5 seconds, so these are the sort of time steps, T1, T2, T3, T4. So in the previous slide there was like xk, so that now it would be x1, x2, and so forth. K denotes the step. And so here we can see that our model with a high sample time, the good thing is that we have less computations, so we need to calculate less power consumed, and also you don't need that. The requirements for the hardware are much smaller, which is good, but then it is very inaccurate because it's sort of losing the actual behavior of the model pretty much altogether. It's not the same at all. It is some sort of an average, but I wouldn't say that this discrete model really portrays the actual behavior of this system. Then we can take another example here on the right side that has the sample time interval is only 2 seconds. So the continuous curve is exactly the same, but we're now computing the state of the system much more often. And this already resembles the actual behavior much better than this previous one with 5 second interval. Of course, there is the downside that then there's more computation, and you don't want to, obviously you could push down the sample time as small as you can get. But if you calculate 1,000 times a second, and there's no actual reason for it, if you're calculating a car, for example, things don't happen. A lot of things don't happen every thousandth of a second. So then you're just using too many computations, and your simulation times get longer, and that's not a smart thing to do. But obviously, then it gets, the lower the sample time, the more accurate your discretized model is. Here in this example, I would still push it to a sample time of 1 second, because here I feel like, especially this sort of S-curve part here, should still have one more dot, and there are still some deviations, especially here, from the continuous behavior. So I would approximate it that it would be a time interval of 1 second, or maybe even smaller. And I hope this gives you some sort of a idea of how do you set up a refresh time interval of your model, or later when we are using the robot operating system, like publishing and subscribing. So how often do you update a velocity command, or how often do you read a sensor reading so that it's still efficient to do it. Okay, so in this entire first lecture, considering the autonomous transportation part and the basics of control, we had the driving task was split into perception, that is basically the area of sensing. Then you have a path plan, and lastly you have control, that is split into longitudinal and lateral. At this point, our focus is in these two. And the perception, you perceive your location, then your distance to things, may they be static like buildings or dynamic like pedestrians, and then detecting the things or classifying the things. So distance is commonly measured with laser or sonar or radar, and then detection and classification is done with machine vision. Then the path plan was split into 3 different phases, or sort of the long-term plan from my house to work. That is split into shorter term plans, such as switching lanes or getting to a roundabout and getting out of the roundabout, or immediate ones that are steering and acceleration or not, should I brake, that sort of immediate actions. And then steering, then control, longitudinal control is acceleration and braking, so going to forward direction, and then lateral is steering, so left and right. And then you have third form, that is reactive, is that if you see a person, then you should stop. If you see a red light, you should stop. If you see a green light, you have to go.